Okay, hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good day. My name is Mama Irsyad bin Fithri Aziz, matrix number B122320049 from section 2 bird 3/1. Okay, so today I'm going to be presenting and showing solutions for my video assignment for my past year examination solution. So my question consists of 4 separate sections. So question A, question B, C, and D, as shown in the screen right now. So we are going to be starting with question A first. So question A, 1 Roman and 2 Roman, consists of basically just theoretical questions. So there's no calculations really over here. So for question A, Roman 1, from chapter 4, actually, we know that there are 3 transient response specifications that we can provide for this question. So it being first, time constant, or we know as tau. 2 is rise time, also known as TR, usually we do in notes. And number 3 is settling time, or TS. Okay, so now moving on to question 2 Roman, what does the performance specifications for a first order system will show? So referring back to chapter 4, shown right now, we know that, and we can see is that time constant will show the time required for the step response to rise up until 63% of its final value. So that is for time constant. For rise time, however, is the time for the waveform to go from 10% to 90% of its final value, or from 0.1 to 0.9 of its final value. And for settling time is it shows the time for the response to reach and stay within the 2% of its final value. So yes, that is for question A. And then we're going to be moving on to question B. Okay, so next we are going to move on to question B. So question B, as shown here, there is a graph. So find the transfer function of the system in figure Q3b. So right off the bat, we have to determine what type of system this is. So right off the bat, it is a first order system. Okay, why? Because the curve is smooth with no overshoot, as shown in the picture in the video right now. So then we can proceed with the general form. Okay, so the general form which is GS equals to K over S plus A. Okay, and then for step 2, we have to find tau, or time constant. As we know earlier, tau or time constant is 63% of the final value. So we know that 63% is 0.63, and the time constant, the final value, the constant settles at 2. The amplitude settles at 2 in the graph. So 0.62 times 2, we have 0.12, and that is tau. So tau equals 0.12 when C is equals to 2. So step 3 is the pole location. Okay, so pole location A is simply just 1 divided by tau. So our pole is A equals 1 over tau. So A equals 1 over 0.12, and our pole location is 8.33. Okay, and next for step 4, finally, we need to find system gain. So system gain K, final value, limit S approaching to 0. So S times 1 over S times K over S plus A. So that is equals to K over A. So 2 equals K over 0.12, and then we will get a total of K, which is 0.24, and then we can finalize that with GS 0.24 over S plus 20. Okay, so next is question C. So question C, for a second order system below, plot their pole location on complex S plane. So for question 1 Roman, G1S equals to 9 over S squared plus 9S plus 9. So right off the bat, how do we approach this question? Approaching this question is simple. We just need to identify the system response by looking at the denominator. So denominator, S squared plus 9S plus 9. We can determine the roots right away. So S equals to negative 9 plus minus negative 4 minus 1, 9 square root over 2, and then we will get negative 9 plus minus 45 over 2, and then we will get negative 1.15, negative 7.85. From this, we know that it is two distinct real negative poles. Okay, so then we are going to plot. We have two negative numbers, so I'm going to plot that right there, and that the negative 7.85 around there, and then we're going to sketch the system response. Okay, and then we determine the response type, which is the response system. It is considered an overdamped system. Okay, next for question 2. So question 2 Roman, G2S equals 9 over s square plus, and again look at the denominator and we can determine that the roots s square plus 9 equals 0. So s is plus minus j3, and then from there we know that it is two imaginary poles, so we can go ahead and sketch that right away. So 3 up there, 3 below there, so because it's plus minus, so 3, and then we're going to plot, and then for the system response we're going to sketch this like so. All of this is are in the notes, so as shown in the screen right now. So this type of system is an underdamped system. Next for question 3 Roman, okay, 9 over s squared plus 6s plus 9, so we're going to simplify that. Okay, s equals to negative 3 and another s is equals to negative 3, so I typoed earlier here, but I will correct it soon. So it is two repeated real negative poles. Okay, the type is are two real negative poles. Okay, so then we are just going to sketch. Okay, so it's at negative 3, both are negative 3s, and then we're going to sketch the system response, and this response is a critically damped system. Okay, now we're gonna move on to the last question, question 3. So given a second order system gs equals 0.04 over s squared plus 0.02s plus 0.04, so find sigma omega n settling time tp and percentage overshoot. So from our lecture notes we can determine the standard form, which is omega n square over s square plus 2 sigma omega ns plus omega n square. So the first step, omega square n equals 0.04, omega n equals to 0.04 square root, so we will get a total of 0.02 radian per second. So the second step is finding the damping ratio. So 2 sigma omega n equals 0.02, then our final value we will get sigma equals to 0.05. So settling time, our syllabus uses a 2% criterion, so which means formula is divided by sigma. So do not use 3. If you use 3, you will lose mark. So ts equals to 4 over sigma omega n, and ts, and then just gonna insert all of the values, and then we will get the value of 400 seconds. So finding peak time, so peak time tp is pi over omega n square root 1 minus sigma square. So we're going to insert back all of the values, and then we will get 15.73 seconds. And then finally for percentage overshoot, we will get using the formula provided in the lab notes, as well. So e negative sigma pi over square root 1 minus sigma squared times 100%. So we're gonna insert all of the values that we have gotten so far, and the percentage overshoot is, we will get finally a total of 85.47%. Okay, so that about wraps up for today's video. To conclude, most of the questions that we did today are mainly from chapter 4 from our lecture notes. So I hope the solutions that I provide is clear, and there are two parts, obviously, like I discussed earlier. The first part is question A, is mainly theory, and then question B, C, D are calculations. So thank you very much. My name is Irsyad, Fithri Aziz, and thank you.